Very much. Enormous pleasure. I think that by now, end of 2018, many people around the world, definitely most of the people here in this venue, have imagined themselves taking their first spin in an autonomous vehicle. We closed our eyes and imagined ourselves gliding down this beautiful road and slowly but cautiously taking our hands off the wheel. And once you take your hands off the steering wheel, that's when the true journey begins. So, autonomous cars are already here, and you have cargo trucks, autonomous cargo trucks already driving on their own special lanes, and even passenger cars. Let us dive deep into what will soon be our reality. All about autonomous driving. Please welcome Professor Amnon Shashua, President and CEO MobilEye, Senior Vice President, Intel Corporation. Please, we apologize for the delay.
You can run an autonomous car.
That's exactly.
So I'll do try. I'll give a presentation without a single slide. Let's see how we can do this. So we're developing autonomous cars, and over time we're looking for barriers. What can be a barrier from going from a science project to really a business? And what we found out, it's not really technology. It's not the level of artificial intelligence we have in our perception. It's not the level of reinforcement learning we have in our driving policy in making decisions. There's something more fundamental that if we do not get a good handle on it, autonomous cars would remain a science project. And what we found out that this particular problem, let's call it a blind spot, calls for a new discipline. And this new discipline, let's call it putting together law and mathematics together, or let's call it regulatory science. And it's all about trying to get a good handle about safety. So when we talk about safety, everybody says safety is paramount, safety is our first consideration, and so forth. But a precise definition of what is meant by safety is kind of elusive. So automotive, they have what they call functional safety. Functional safety is about making sure that you have system integrity, that if there is a bug in your software or a malfunction in your hardware, you have a way to detect, you have a way to go to a secondary channel, a fail operation. It's all about bugs. But now when you want to move an autonomous car, it's not the bugs that you are concerned about, is what kind of assurances one can give to society about whether these machines are going to be involved in accidents, are going to kill people, and how to do it in a way that gives comfort to society. And one of the first conclusions that you come up with, that in order for society to accept autonomous cars, you need to prove actually that you'll be orders of magnitude safer than humans. Because humans, there's lots of fatality with humans. So when we started looking at what exists out there in terms of providing safety assurances, the kinds of approaches did not satisfy us. And because of lack of time, I'll not go over the approaches. I'll simply explain what we're doing there. Okay, I'll continue. Actually, I'm on the run. We don't need this presentation. Okay. So when you look at the law, right, about the guidebook of how to drive, everything is clear until you reach a point which is very elusive and ill-defined, and it's called the duty of care. Now, the duty of care is not just for automotive. It's for any business that could harm people. So if you are in a business that could harm people, you should exercise care. Now, what is meant by exercise care is left for interpretation. And it's left for interpretation, actually every law is left for interpretation, but this particular law, the law of duty of care, is very, very critical. Because if we don't understand, if the machine doesn't understand what is meant to be careful, then how could we put an autonomous car on the road? And then we started asking ourselves, okay, is defining what being careful is simply a philosophical question? It turned out that it's not just a philosophical question, it's a philosophical plus mathematical question. And I'll try in the next 5 minutes to give you this sense of why it's a mathematical question. So, if we want to provide an interpretation that is good for machines, for the duty of care, then we need to optimize 3 axes. 2 of them are kind of obvious, the third one is completely non-obvious. So the first axis is that the interpretation must be sound. Sound meaning that it should comply with the common sense of human driving. The way humans interpret care, or the way humans interpret being careful, should also comply with the way the machine interprets careful. Right? Because we want the machine to comply with the way humans drive on the road. So you want to be sound. But you can be sound, but not being useful at all. So I'll give an example of a legitimate interpretation of duty of care, which is completely useless. So I can interpret duty of care by saying that, when I change lane, I should not interfere with the motion of other road users. Right? Sounds legitimate, I'm very, very... I merge into traffic without affecting anyone's motion. Nobody's affected by my own motion. This sounds perfect. But, try driving in Israel like this. Nobody will let you change lane. And in many countries like France, like Italy, like Boston, Los Angeles, most of the places in the world, you cannot make this assumption. So if you make this assumption, it sounds like a good interpretation of being careful, but it's useless. So there's another axis to optimize, and that's the agility. You should be able to have an interpretation which allows agility of the autonomous car. Okay, so we want, on one hand, to be sound, another one to be agile. Now comes the third. The third axis, this is where really mathematics should come in. You need to prove that whatever interpretation you have, you need to prove that you can verify its implementation in the machine in a robust way, in an efficient way. So I'll give you an example of a negative example. Let's assume my interpretation of being careful says that if a car behind you is too close to you, then accelerate a bit. Sounds reasonable. We also, humans, sometimes do it. If we see in the rear mirror that the car behind us is too close to us, is tailgating us, we accelerate a bit. The problem, if this is a rule, if this is part of your interpretation, you can never use the inductive principle, because then, in order to verify that your action is safe, that your action is proper, you need to compound. You need to look at all agents simultaneously, and then you'll have butterfly effects. Butterfly effects meaning you can make an innocent action now, and then later in the future it will cause an accident. So you can never verify that the action that you are making conforms to the interpretation of being careful. So we call this efficiently verifiable. You need an interpretation that on one hand is sound, the other hand is agile, third is implementable in a machine. And these three axes, optimizing these three axes is kind of tricky, and this is where mathematics is important. So we set out a year ago to write a model and make it open. So it's true that MobilEye is kind of a closed system. We're always closed, but in this case we decided to be open because it is important for the entire industry to clarify all of this, so for the entire industry we'll be able to put cars on the road, and then we compete on the technology, but at least the definitions of what is meant to be careful will be shared among all of us. So we wrote it as an academic paper. We are now at the fourth revision of this paper, where we set this interpretation. The interpretation is based on the Occam's razor principle. So all the driving experiences, all the complexity of driving experiences is reduced to five basic principles, like right of way is given, not taken, be careful from occlusions, about keep safe distance to the car in front of you. And then you can show that the complexity, like priority rules and so forth, are simply derived from a very simple set of five principles. And then we set up the interpretation in such a way that it is efficiently verifiable, so that we can prove the induction principle on whatever we do. And what this basically does, it says the following. It defines what dangerous is. Because if the machine doesn't know, it doesn't have a formal definition of what dangerous is, it can never be agile. Because if you don't know what dangerous is, you become conservative. Because you don't know if this action that you're going to make is going to cause an accident or not cause an accident. So you need this formal definition of what dangerous is. And today, there is no formal definition of what dangerous is. For example, if I change lane and the other car hits me, we will go to court and we'll have two stories. My story would be that this guy was inattentive. His or her story is going to be that I was reckless. And it's then a matter of the judge and jury and so forth to analyze my interpretation of duty of care and so forth. So a machine needs to know what dangerous is. Second thing, the machine needs to know what is a proper response if you are in a dangerous situation. And this proper response should be efficiently verifiable. It means that whatever response you're doing, if you conform to the model, there are never going to be butterfly effects. There's never going to be a chain of chain of reactions that eventually in the future will lead to an accident of your fault. Right? And third is what assumptions are you making about other road users? Because what is duty of care? Duty of care basically says that you are making assumptions about what other road users are doing. So on one hand, you are taking the worst case, but it's a worst case under certain assumptions. So I'll give you an example and I'll end here. Let's assume I want to keep safe distance to the car in front. Now, if the car in front can brake instantaneously at infinite G, not 1G, 2G, so infinite G, physically it's not possible, but for the sake of argument, at infinite G, basically I'm assuming that the car in front of me is stationary on the road. If the car in front of me is stationary on the road, I need to keep quite a long distance to it. And that'll become non-useful, right? Because all other road users will overtake me, right? So I need to make an assumption of what is the maximal braking force a car in front of me can make. So this is an assumption. This assumption should be vetted with regulatory bodies, right? Or this assumption should be analyzed through data. Should I make the assumption that the car in front of me maximum brakes is 0.6 G, 0.8 G, 1 G? It will determine what safe distance I can make. I need to make an assumption of what is my response time. Me as a computer, I know what's my response time, but I need to make an assumption what are the human driver's response time. Is it half a second? Is it 1 second? Again, this should be vetted with regulatory bodies. So we do make assumptions. And those assumptions under a worst case scenario meaning the car in front of me all of a sudden applied maximum brake. That's a worst case. But worst case plus assumptions really defines what is the interpretation of duty of care. And this is what we set in that article. We're working with regulatory bodies in the US, Europe, China. Baidu officially translated this interpretation. It's called RSS, Responsibility Sensitive Safety, into Chinese and officially adopted it. We're working with industry players like our customers, OEMs, and tier ones, and even our competitors, in order to coalesce around a model which would allow everyone to put an autonomous car on the road. So, what I had in my presentation is also some nice movies about how our car in Jerusalem drives. So there is no movie, but I'll explain a bit. We are developing our system and testing it in Israel. And one of the reasons for testing it in Israel is because of the culture of assertive driving here in Israel, which, as I said, is similar to France, Italy, and Boston. And specifically in Jerusalem, there's another factor which is, it's like San Francisco, it's hilly. You know, Jerusalem is on a mountain, so it's hilly, so it's not just flat. And we have our autonomous car driving in the city in a way that's very, very agile, conforming to this RSS model, so it will never cause an accident. And we even, have what we call an AV Turing test. So a guy in the back seat, guy or a woman in the back seat, needs to say at the end of the drive whether the machine was driven by a human or by the AI. And sometimes it's very, very difficult. It can maneuver, change lane in an assertive way, assertive but yet safe, in a way that when you sit in the back seat, you don't know whether it's a machine or a human driving. Okay? Oh, thank you. Sorry for the no slides, but I hope it was interesting.